And what we're going to start is we're going to start reaction stoichiometry. Basically, stoichiometry is just a fancy name for chemical mathematics. So in other words, it's mathematics associated with chemical. We have developed a variety of conversion factors that we can use with stoichiometry. Those conversion factors have included Avogadro's number. You use Avogadro's number anytime you're talking about an atom, an ion, a molecule, or something of that nature where we're talking about a single entity within a substance. There is the density. The density is used anytime as a conversion factor anytime you're needing to go between the volume of a pure substance and the grams of a pure substance, meaning the volume of ethanol to the grams of ethanol, or the volume of isopropyl alcohol to the grams of isopropyl alcohol, meaning that the starting substance and the ending substance is the same material. That takes us to the mass. Anytime I see mass, I automatically think molar mass as the conversion factor because that's going to typically be your conversion factor. And then finally, we get into the mole-to-mole ratio. The mole-to-mole ratio is the only acceptable way to convert between two unique substances. And how do we know that they're unique substances? It's because they have different formulas. Now, we briefly talked about one yesterday, which we'll bring up again, hopefully Thursday, and that is molarity. Molarity represents yet another conversion factor. Molarity allows us to convert between the volume of a solution and the moles of that material. So, different volumes here. Pure substance compared to a solution. It all depends on what you're wanting to work with. Now, the best way to get into this is actually to do some conversions. So how many moles of carbon are required to react with 6 moles of cobalt-3 oxide in the reaction where 2 cobalt-3 oxides plus 3 carbons goes to form 4 cobalts and 3 carbon dioxides? Okay. We figure out what we have been given. We have been given 6 moles of cobalt-3 oxide. And we figure out what we have been asked to solve for. We've been asked to solve for the moles of carbon. Because cobalt-3 oxide and carbon have different formulas, the only acceptable way to convert between these two is going to be a mole-to-mole ratio. Now, when you're talking about a balanced chemical equation, the mole-to-mole ratio comes from the coefficients of the balanced chemical equation. So this literally says 2 moles of cobalt-3 oxide will react with 3 moles of carbon. So the first thing I did was I looked at the substance, and again, because the substances were different, that is why I went to the mole-to-mole ratio. The next thing I would typically look at is I would look at the unit that I was given. I was given moles. Great. I already have moles. I would look at the other unit I was given. Moles. Great. I already have moles, meaning the mole-to-mole ratio is the only conversion factor I'm going to need in order to accomplish this task. Now, to set up the calculation, I have 6 moles of cobalt-3 oxide. Of my mole-to-mole ratio, the cobalt-3 oxide is going to go in the denominator. With the moles of carbon in the numerator. The moles of cobalt-3 oxide went in the denominator so that the unit and the substance would cancel, leaving moles of carbon. When you do this math, you get 9 moles of carbon, which is what the question asked us to solve for. Questions? Again, I knew I needed the mole-to-mole ratio because the two substances were different. Okay, let's look at a more complex problem. How many grams of carbon dioxide are emitted upon the combustion of 3.9 times 10 to the 15 grams of octane? Okay, and I'm given the balanced chemical equation. So I start with what I was given, which is 3.9 times 10 to the 15 grams of octane. The next thing I do is I figure out what I need to solve for. I need grams of CO2. Octane and carbon dioxide have different formulas. Because they have different formulas, the only acceptable way to convert between the two is the mole-to-mole ratio. So I'm going to need a mole-to-mole ratio, which is going to come from the balanced chemical equation. For every 2 moles of octane that react, we get 16 moles of carbon dioxide. Again, I knew I needed that mole-to-mole ratio because the formulas were different. The next thing I note is the unit is grams. Anytime I have grams, anytime you have grams, you're automatically going to think molar mass. So I need the molar mass of octane. That is 8 times 12.01 plus 18 times 1.01. Or in other words, we're talking about 114.26 grams of C8H18 is equal to 1 mole of C8H18. The next thing I note is I need grams of carbon dioxide. Again, anytime I see grams, it means that I'm going to need the molar mass as a conversion factor. This time I need the molar mass of carbon dioxide, which is 44.01 grams of carbon dioxide is equal to 1 mole of carbon dioxide. Basically, folks, I took that, what I had and what I needed, and I picked it apart to identify possible conversion factors I'm going to be using in this conversion. Now, to begin with the math, I have 3.9 times 10 to the 15 grams of C8H18. My first conversion factor is going to need to have grams of C8H18. Therefore, I'm going to be using the molar mass of C8H18. Of that molar mass, the gram portion is going to go in the denominator with the mole portion in the numerator. The gram portion went in the denominator so that the unit and the substance would cancel out, leaving me moles of C8H18. Now I can use the mole-to-mole ratio to convert between moles of C8H18 and moles of CO2. There are 2 moles of C8H18 for 16 moles of CO2. Now, the moles of C8H18 went in the denominator so that the unit and the substance would cancel, leaving me moles of CO2. Now I can use the molar mass of CO2 in order to convert that into mass of CO2. For the molar mass, the moles of CO2 go in the denominator with the 44.01 grams of CO2 in the numerator. Again, the moles of CO2 had to go in the denominator so that it would cancel out. And I'm left with grams of CO2. I'm now ready to key this into the calculator. And when you key this into the calculator, you get a value of 1.2 times 10 to the 16 grams of CO2. Now, I want to make note of a few things. Number one is that when you're working with these types of problems, whatever the information is in the actual problem itself is going to dictate how many significant digits you have. That is because it depends upon which periodic table you go to determine the molar mass as to how many digits it gives you. So again, the number in the background or in the actual information is typically going to determine your number of significant digits. Now, the second thing I want you to note is that when you're talking about molar masses, the mole portion of the molar mass has an unlimited number of significant digits. It's an exact quantity. I also want you to note that the mole-to-mole ratio are exact quantities. Therefore, they have unlimited number of significant digits. Again, because of those facts, the only things that could potentially play into our significant digits is our starting quantity in our molar masses. And again, it all depends on what periodic table you look at as to whether the molar mass is going to impact the significant digits or not. So typically just go to your starting quantity. The second thing I want to make note is something that hopefully you'll be appreciative on a test. There will be a separate molar mass question. There will be a separate balancing chemical reactions question. But when it comes to actually doing stoichiometry on an exam, you will be given the balanced chemical equation and you will be given the molar masses. You just have to know how to use them. That is because I don't want you to build a calculation off of faulty information. And so I'm going to start it out with all the correct information. You just have to know how to use it and when. Questions? Okay. Reaction stoichiometry. The reason I breezed through that last problem and didn't do the last problem is because we're actually going to get more practice. Because what we're going to do next is we're going to get into limiting reactants. And limiting reactants is going to use reaction stoichiometry. Now, we're going to talk about a variety of things in this particular slide. The first is the concept of a limiting reactant. The second is the concept of theoretical yield, which is going to require us to understand actual yield. And the actual yield and theoretical yield are going to be used in determining the percent yield. And then there's the reactant in excess. The reason we cover limiting reactants is, for the most part, when you're upstairs, you mix chemical A with chemical B. In other words, you're starting out with a specific quantity of chemical A and a specific quantity of chemical B. When those two chemicals combine, somebody is going to run out first. You're going to run out of one of them first. That chemical that you run out of is going to be considered the limiting reactant because it limits the reaction. It's kind of like the making of hot dogs. You got 5 hot dogs, you got 4 buns. The maximum number of hot dogs that you can make is going to be 4. Because at that point, you ran out of buns. In this particular case, the buns were the limiting reactant because that is the chemical that we ran out of first. Now, the theoretical yield is all based off of the limiting reactant. The theoretical yield says, in theory, this is what I can make. Now, it's purely theory because there's a lot of side reactions that could go on. But in theory, the limiting reactant is going to control the theoretical yield. And then you're going to have a reagent that's in excess, which literally is going to be whatever substance is left over after you've created your theoretical yield. So if we're talking about chemicals, we can think of iron reacting with sulfur to make iron sulfide. Here we have 4 iron atoms reacting with 3 sulfur atoms. When they combine in a 1-to-1 ratio to make iron 2 sulfide. This sulfur is our limiting reactant because once sulfur ran out, we can no longer make iron 2 sulfide. The iron was the element in excess. And then our theoretical yield would be 3 iron 2 sulfides. So you can think of it as hot dogs and buns, or you can think of it as atoms and molecules. The theory, the terminology is going to hold. So your limiting reactant is the reactant that is completely consumed in the chemical reaction and limits the amount of product that can be formed. The reactant in excess is going to be any reactant that occurs in a quantity greater than is required to completely react with the limiting reactant. The theoretical yield is going to be the amount of product that can be made if in the chemical reaction based on the amount of limiting reactant. This theoretical yield, as we'll talk about, is assuming perfect reaction. It's assuming nothing else goes on in the chemical reaction. In reality, side reactions always occur. And so we have an actual yield. This is the amount of chemical that is actually made. Now, in a problem in the classroom, whether it's on an exam or in the problems that I'm going to give you, I have to give you that number because typically that number is determined in the laboratory. And then finally, the percent yield. The percent yield, the equation for the percent yield is that it's the actual yield divided by the theoretical yield times 100. Folks, percent yields drive business. It is the job of a chemist, typically, to develop possible ways in order to make product that manufacturers are trying to sell. Chemists are always looking for better ways to make product that the manufacturer wants to sell. How do we determine whether our method that we have developed is better or not? And the answer is the percent yield. We are looking for a reaction that drives a higher percent yield. Now there is going to be the factor of percent yield compared to cost analysis. But for the most part, as somebody in industry, our goal is to drive this percent yield, to increase this percent yield at preferably a reasonable cost. Because the percent yield means we're making more product that the manufacturer can therefore sell. Okay, so limiting reactive problems. What is the process for performing the calculations? There are a couple of different ways that you can do this, but the one that I find the easiest is we're going to convert each reactant into grams of the target product. In other words, we're going to perform the exact same calculation we just performed, but we're going to perform it for reactant A to that product, and we're going to perform it for reactant B to that product. So we're going to convert each reactant into the grams of the target product. Once we do so, we're going to identify the lowest mass of target product produced. That is going to be your theoretical yield. That lowest mass of target products that can be produced can be traced back to the limiting reactant, because it's going to be the reactant that ran out first. Basically, once you make that amount of product, you cannot make any more. It doesn't matter what else you have in that vat. You can't make any more product once that limiting reactant has been used up. So let's apply this. A reaction mixture contains 42.5 grams of magnesium and 33.8 grams of oxygen. What are the limiting reactant and theoretical yield? The reaction we are studying takes 2 magnesium, reacts it with oxygen to form 2 magnesium oxides. Okay, when I look at this, I see I have 42.5 grams of magnesium. I have 33.8 grams of oxygen. Right off the bat, I notice I have mass of 2 reactants. That is your sign that you're dealing with the limiting reactant problem. If you have mass of 2 reactants, you're dealing with the limiting reactant problem. So I'm going to convert this into grams of magnesium oxide. So the first problem I want to do is going to require me to convert 42.5 grams of magnesium into grams of magnesium oxide. The second problem is going to require me to convert 33.8 grams of oxygen into grams of magnesium oxide. Conversion factors that I'm going to need. Well, my starting formula and my ending formula are different. So one of the conversion factors I'm going to need is I'm going to need a mole to mole ratio. Another thing that I notice is I'm starting out with grams of substance. Anytime you're starting out with grams of a material, you're going to need the molar mass. Well, the molar mass of magnesium is 24.31 grams of magnesium is equal to 1 mole of magnesium. I am converting that into grams of magnesium oxide. Magnesium is 24.31 and oxygen is 16. So therefore the molar mass of magnesium oxide is 40.31 grams of magnesium oxide is equal to 1 mole of magnesium oxide. Again, folks, I started by looking at what I was given and what I needed to solve for, and I picked it apart to identify possible conversion factors. We're going to begin the problem with the piece of information that we have been given. So we're going to start with the 42.5 grams of magnesium. Our very first conversion factor is going to need to have grams of magnesium. So I'm going to use the molar mass of magnesium. So that's 24.31 grams of magnesium is equal to 1 mole of magnesium. The grams of the magnesium go in the denominator so that the unit and the substance will cancel out. Now I have moles of magnesium and I need to use the mole-to-mole ratio in order to convert from magnesium into magnesium oxide. According to the balanced chemical equation, 2 moles of magnesium produce 2 moles of magnesium oxide. The mole of magnesium went in the denominator so that the unit and the substance would cancel out, leaving moles of magnesium oxide. But I find it easier. Now, you can actually convert to and stop here on both calculations, but it usually means you got to do another bit of math after this. So I find it easier just to go ahead and do that bit of math, which is taking the moles of my material and converting it into grams of the product. So I'm going to take that moles of magnesium oxide and I'm going to convert it into grams of magnesium oxide, with the fact that 1 mole of magnesium oxide is equal to 40.31 grams of magnesium oxide. And I'm ready to calculate. And when you calculate, you get a value of 70.47 grams of magnesium oxide. But this is a limiting reactant problem. You cannot just do one calculation. You have to do a second calculation. You have to convert that second reactant into the desired product. So we're going to convert the 33.8 grams of oxygen into grams of magnesium oxide. Our first conversion factor is going to be the molar mass of oxygen. According to the formula, that molar mass is 32.00 grams of oxygen is equal to 1 mole of oxygen. The grams of oxygen went in the denominator so that the unit and the substance would cancel out. Now I'm going to use the mole-to-mole ratio, which is going to come from the balanced chemical equation. For every 1 mole of oxygen that reacts, you get out 2 moles of magnesium oxide. The oxygen went in the denominator so that the unit and the substance would cancel out, leaving moles of magnesium oxide. But again, we're going to go ahead and convert it all the way to grams of magnesium oxide. By multiplying that by 40.31 grams of magnesium oxide in 1 mole of magnesium oxide. The mole of magnesium oxide went in the denominator so that the unit and the substance would cancel out, leaving me grams of magnesium oxide. That was 33.8. And when you complete this calculation, you get 85.15 grams of magnesium oxide. Okay. You've performed the calculation, but we haven't actually answered the question. What is the limiting reactant and what is the theoretical yield? What you're going to do is you're going to look at the two numbers that you obtained. You obtained 70.47 grams of magnesium oxide and 85.15 grams of magnesium oxide. The one that is in the lowest quantity is your theoretical yield. And that theoretical yield can be traced back to the limiting reactant. So what did this math show? And what can we say about the math? Number one, this math says that if all 42.5 grams of magnesium is used up, the maximum that can be obtained is 70.47 grams of magnesium oxide. That's what that math means. Something I want you to know. You cannot simply look at the smallest mass in your problem and that tell you who the limiting reactant is. You have to do the math, folks. Because just because it is the smallest amount does not mean that that's the limiting reactant. There are other factors that come into play. Something else that I meant to point out on the previous problem that I did not is this mole-to-mole ratio is the only time you take into account the coefficients. You don't take into account the coefficients in any other part of the math problem except in the mole-to-mole ratio. Again, the only time we take into account the coefficients is in the mole-to-mole ratio. We don't take into account the coefficients in any other portion. Questions about this problem? Okay, so this is an addendum to that last problem. After the synthesis, what we found out is that the actual yield of magnesium oxide was 55.9 grams. What is the percent yield? Percent yield is a formula, folks. Percent yield is the actual yield divided by the theoretical yield times 100. The actual yield is going to have to be given in the problem. And you calculate the theoretical yield. And that's multiplied by 100. So the percent yield in this particular reaction was 79.3% for the formation of magnesium oxide. Questions? Let's look at another example. I want to give you a moment or a few minutes to work out this one on your own. You're going to use the same process that we used. So I'll help you get started. We are told that we had 28.6 kilograms of carbon reacting with 88.2 kilograms of titanium oxide. This tells me it's a limiting reactant problem because I have mass of both reactants. And I formed 42.8 kilograms of titanium. When it says the word formed or produced, that means that this is your actual yield. What is the percent yield? Well, find the limiting reactant, theoretical yield, and percent yield. In case you don't have your periodic table readily accessible, titanium has a mass of, where is titanium? Ti. Should be right there. Titanium. Oh, there it is, 47.88. And oxygen is 16. And carbon is 12.01.
Oops.
Okay, let's see how it's going. The first thing I did is I realized that this had to be a limiting reactant problem because I had starting quantities of both masses, of both substances. So I took the titanium core oxide and I converted that into titanium. 88.2 kilograms of titanium core oxide, converted that into grams, and then used the molar mass of titanium core oxide to convert that into moles of titanium core oxide. I then used the mole to mole ratio from the balanced chemical equation. There's 1 mole of titanium core oxide for every 1 mole of titanium. I then used the molar mass of titanium to get that into grams of titanium and ultimately into kilograms of titanium to be 52.87 kilograms of titanium. But again, this is a limiting reactant problem. You have to convert both reactants into the actual product. So I also converted the carbon into titanium. And when I converted carbon into titanium, I got 57.01 kilograms of titanium. I looked at which one was the smallest. And it was the 52.87 kilograms of titanium. Because the 52.87 kilograms of titanium was the smallest, that is your theoretical yield. The theoretical yield can be backtracked to your limiting reactant. That is the reactant that's going to run out first. I also use the theoretical yield in the percent yield calculation, which is actual yield, which has to be given to you, divided by theoretical yield times 100 to get 81%. Question. Because this is going to be on the test next Tuesday, let's do one more problem of this nature. That's a 55.85. I know it's rather small in the back. Okay. So I noticed I had 167 grams of iron oxide, and I had 85.8 grams of carbon monoxide, meaning I had masses for both reactants. That should scream it is a limiting reactant problem. Meaning you're going to convert both reactants into the desired product. In this case, because I said that it produced 72.3 grams of iron, I'm telling you the desired product is iron. So I converted the 167 grams of iron 3 oxide into iron by starting by using the molar mass of iron 3 oxide. The molar mass allowed me to convert it into moles of iron 3 oxide. Once the moles of iron 3 oxide, I used the mole-to-mole ratio from the balanced chemical equation to convert that into moles of iron. And then I used the molar mass of iron to get it into mass of iron. I did the same thing with the carbon monoxide. I started out with a mass of carbon monoxide. I converted that into moles of carbon monoxide using the molar mass of carbon monoxide. Then I converted the moles of carbon monoxide into moles of iron using the mole-to-mole ratio from the balanced chemical equation. And ultimately, I got it into mass of iron using the molar mass of iron. Looking at the two numbers, the one that was in the smallest quantity was the mass produced from the carbon monoxide. Therefore, the carbon monoxide was the limiting reactant, and the mass that carbon monoxide produced was the theoretical yield. I then put that into the percent yield equation in order to convert the actual yield divided by the theoretical yield times 100, and it gave me 63.4% for the percent yield. Question. This is where test 3's information stops. However, Thursday we will be moving on. We will be dealing with concentrations. Now, I had several people ask me when the lab that we did yesterday is due. So I did look that up this morning, and it is due Monday when you come to lab. So it is due Monday when you come to lab. Any questions for me? If not, I will see you on Thursday.